Now, the lecture that you've chosen for me to present here in beautiful Vancouver, or beautiful Burnaby, I guess, we're not actually in Vancouver right now, is this presentation on geomechanics of trenchless pipe installation, repair and replacement. And of course, in the time I've got to present to you this evening, I can only introduce you to some of these concepts. And I've chosen to introduce you to one specific trenchless pipe installation technology, one specific pipe repair issue, and one specific pipe replacement technology as a way of illustrating how important the geomechanics are, to give you some insight into what I've learnt, and also to introduce you to some of the tools that my students and I have been working hard to develop, tools which consultants, geotechnical consultants, can deploy and assist them in doing design and monitoring of projects. But let's talk a little bit about why we use trenchless construction. This mighty city here that you see with these 2- and 3-storied buildings, this broad thoroughfare, is Princess Street, Kingston, my hometown. And this is actually taken in 2013. I actually had to pay a license fee to have access to this image, to Sun Media. But basically it shows the reconstruction of Princess Street in what we call the Big Dig. And of course, it's not exactly Boston's Big Dig, but we call it the Big Dig in Kingston. And it's awesome. It's absolutely awesome. Look how we get to see all the pipe systems that are crossing under Princess Street and down Princess Street. The water supply pipes, the wastewater, stormwater pipes, and the conduits, of course, that carry the electricity, gas, steam, and communications that we rely on. And it's fantastic if you're somebody like me to go to a site like that. But you know, somehow the rest of the community doesn't feel quite as positive about it. They think it's a big, ugly mess. And if you're a shop owner in one of these, like this general store here, and your customers can't reach you, you can be bankrupt in 4 to 6 weeks. Now, of course, the contractor in the city makes special arrangements to at least facilitate some access to those properties. But, you know, maybe there's a better way. And of course, there is. Of course, well, maybe I'll just backtrack a little bit. There are times when you need to just rip it all out and replace it all. And that's the logical thing to do. But there are many circumstances where you need to just maintain or replace or install a single pipeline, in which case this type of operation is brutally inefficient. And so, of course, trenchless construction, or the so-called trenchless technologies, offer us a range of methods, and it's growing every year, that clever, creative contractors have developed for doing all these operations. And here's some photographs illustrating some of that. So here's a drilling rig. It was a project that one of my former graduate students was monitoring under the North Saskatchewan River, installation of a large oil pipeline using directional drilling. Here's a shot of an operation at the RCMP Academy in Ottawa, Ontario, where they were replacing a concrete sewer with a polyethylene sewer replacement. This picture here is actually taken in our laboratory, where we were testing or doing research on a new culvert rehabilitation procedure, basically sprayed lining. This was a contractor that came up from Michigan to trial this particular product. Here's a slip liner that's just before, so for a culvert rehab project in Northern Ontario, being inserted into an old corrugated steel structure. Then there'd be grouting put in between. And down here, simple invert paving. So you put a slab of reinforced concrete in the bottom of a corroded corrugated steel structure. Now, those methods all allow you to do the operations without cut and cover construction. Another reason why I'm showing you this particular set of pictures is because I wanted to emphasize that a lot of the research that's done in this area relates to structural engineering. But the topic of my presentation this evening is not the structural mechanics of trenchless construction. And so even though maybe 70% of my research is on the structural side, I'm going to be focusing on some very specific issues that relate to geotechnical engineering. So here's my objectives. Obviously, make that introduction. I mentioned earlier that I'm going to be illustrating 3 different technologies, but it's also an opportunity for me to show you how we can combine analytical work, computational work, and most importantly, I think, experimental work to develop design tools that contractors and, more importantly, geotechnical consultants can employ. And I'll be talking a little about or showing you a little bit of the progress that we've made in these areas. And once or twice during the talk, I'll also comment on some of the remaining research needs. So the 3 technologies that I mentioned, pipe installation using directional drilling. Specifically, we're going to look at the mechanics of mud loss. And that's the first topic, and I'll explain that in detail in a moment. Pipe repair. Normally, when we're repairing a damaged sewer or a damaged culvert, damaged water pipe, we're primarily focused on the pipe structure. But in fact, deterioration can extend into the soil. And that deterioration, the most important sort of deterioration of the soil is erosion. And so I'm going to specifically talk about the impact of erosion voids on the pipe and the stability of the overlying pavement, and repair using grouting. Is it effective to grout those voids? Does it return the system to its pre-damaged state? And then I'm going to finish up with an illustration of pipe replacement using static pipe bursting, specifically focusing on the topic of ground disturbance. And these are all geotechnically oriented topics. So how many people here have some knowledge of directional drilling? So maybe a third of the people here. So I'll take a minute or so just to explain what directional drilling is. We have a drilling rig, a little bit like the one that I showed on an earlier picture, where the drill string is angled down, and the contractor can steer the bit, and also there's a location technology. So the contractor knows where the tip of the drill string is during the operation. And using those two capabilities, basically you design a drill path. It should consider the geology of the site. So you should be doing characterization. And I was having a conversation with somebody earlier about how, in fact, many times the contractor just goes for it with no knowledge of what the local geology is. But for a river crossing, you'd be crazy to just try and attempt a river crossing without doing site characterization. But basically, you'll figure out which way you're going to go, and then the contractor will drill down under the obstruction back up to the surface. This could be a river, it could be a highway, a railway. It might be an environmentally sensitive area. It might be a contaminated site where you don't want to be excavating and then having to deal with contaminated soil. And you can get close to that design exit point within I'll say inches, but within a meter or so, without too much difficulty. And so that's the pilot hole. And then you'll attach what's called a reamer, which is basically another bit that enlarges the borehole. We have to make the borehole big enough that the pipe can fit through it. And so then it'll be reamed back, and that might be done in one operation. It might be done in multiple operations if you have to create a very big borehole for a very large pipe. And then at the very end, the contractor will drill right back down through the borehole again, grab onto the new pipe over here, and then pull the new pipe into place. And you can see in this little illustration here that the pipe is partly pulled into the borehole. Now, drilling mud is a requirement in these operations. Now, sometimes contractors will do it with water, just using water. Not a smart idea, but generally speaking, most contractors will use drilling mud. So we're talking bentonite. It's got additives, which I don't have time to talk about tonight. And this is in fact the mud pit for that big drilling machine for that project under the North Saskatchewan. And at the end of the drill string, the mud's being ejected, or it's being injected into the borehole, and then it's being pumped back up to the surface. And it's bringing with the cuttings from the borehole. The mud is stabilizing the borehole so it doesn't collapse. It's going to lubricate that pipe during that last operation where we're pulling the pipe into place. It also cools it. But unfortunately, the mud pressure can exceed the strength of the surrounding soil so that it loses confinement. And then you get what's called, in a slightly sort of la-di-da description of it, inadvertent returns, okay? Of course, what the contractor calls it is frac-out. That's the common expression. Now, it's not actually normally hydrofracture. They call it frac-out. It's not normally hydrofracture. We'll talk about that in the next few minutes. And this is a picture I got off the internet. It's not one I actually took, hence the reference here. But this is in front of somebody's house. There's their car. Their property is just up here. This is the curb of, and this is the big mess that's created, as in this particular case, there was some inadvertent returns. Now that's one thing, but if it comes up under a railway line or under into a river, if it, it's not good. And so it needs to be controlled. Now you can also get surface uplift. So this operation can cause the ground surface and ground deformations. And I'll say a few things about that this evening, but not very many. The main thing that I'm going to be focusing on is this issue of preventing inadvertent returns. And I'll have one slide to talk about what causes pressures, where does the pressure come from, and then we'll have quite a few slides talking about how much pressure can the soil resist before it basically can't confine the mud and it works its way up to the surface. So the slide on where does the mud pressure come from, one way of thinking about it is just simple hydrostatics. So we've got a fluid, a mud that has a density, and there's a mud column to the surface. Let's say we're down at this location here. It's a certain depth below the pit entry up here. And that height of mud times the depth, times the unit weight of the fluid gives you the pressure, hydrostatic pressure. The fluid density is a function of how much cuttings there is in the material, which is a function of how much effort the contractor makes to clean that mud as they're doing the operation. Also, the mud is flowing, and flowing fluid has viscosity. And so just the act of the fluid flowing creates more pressure, okay? And so this is not a talk, however, about fluid mechanics of trenchless construction. So this is all I'm going to say about it, and it's not really my area of expertise. But I will again comment on that the viscosity of the mud is a function of how much effort the contractor goes to clean the mud. And so, of course, the less effort, the cheaper it is for the contractor, but the more risky. So contractors know this stuff, experienced contractors, and they make judgments as to whether or not they need to do more effort and so on. And well, we'll talk a little bit more about that as we go along. Now, I wanted to also introduce you to the three, or how I've sort of defined the three mechanisms of mud loss. And the first mechanism, the commonest mechanism, is shear failure or blowout. So what happens is we've got fluid under pressure in this borehole. It basically causes the surrounding soil to go into a state of shear failure. And if that shear failure reaches the surface, then we've got this sort of unconfined plastic region, and we'll have blowout. We can get tensile fracture in clay soils, not in sands, but in clay soils. And essentially what's happening here is that that internal pressure from the mud is acting to stretch the borehole or stretch the soil around the borehole. And because it's stretching, it's going into incremental tension. And if that incremental tension exceeds the initial compressive stresses in the ground, it will go into tension, into absolute tension, right? And so once it's in tension, soil doesn't like tension, it'll crack. And once you have that crack initiation, rapidly the crack will propagate to the surface, and you'll have an inadvertent return. We also have heterogeneities at the site, which are a function of the geology and other infrastructure, typically. And this is my sort of somewhat lame attempt to represent a plane of weakness in the soil, where there might be some feature, geological feature, where the mud can flow up that feature, okay? this is my attempt to represent what happens when you get interaction with existing infrastructure. And a very common circumstance is when the mud sort of finds at the sides of a telegraph pole, because it's much easier for the mud to work its way up between an existing interface between, say, soil and a structure, where it doesn't have to break the soil. It just has to exceed the initial compressive stress. That's much easier than to actually exceed the shear strength. You can see it coming up beside basements and things like that. So these are heterogeneities. Now, I'm not going to say anything more about this. This is a function of the specifics of the site. And I'm going to focus on these two mechanisms and largely speak about uniform materials. And I'll say something about stratified materials a little bit later. Now, we're going to talk about sands, and then we're going to talk about clays. And the reason I start with sands is because I've got some very beautiful experiments that I can show you. And those experiments are very valuable because we will be able to actually see what the mechanism, the actual flow of mud to the surface through the sand. Those experiments have been used to develop computer models and undertake parametric studies. We'll touch on that briefly because I've got a lot to get through tonight, and develop simple design equation, which then you can program into a spreadsheet. So that's kind of the objective of the research. This work performed by 3 students, David Elwood, Hongwei Shah, who was in the audience when I was presenting this in Edmonton on Wednesday or Tuesday, whenever it was, Tuesday, I guess it was, and Haitao Lan, who was in the audience when I was presenting this in Toronto, which was lovely. But I'm going to focus on Haitao Lan's experiments. So this has just been published in the American Journal of Geotech and Geoenvironmental. And let's look at the profile. He did his experiments in the smallest test pit at Queen's, 2 meters wide, 2 meters deep, 4 meters long, a 38 millimeter borehole. 38 millimeters is the diameter of a Shelby tube, or at least the ones that we have. And that's how we cut the borehole and basically pump the borehole full of mud. Let's look at this view. It's a bit more informative. Here's a bulkhead that was built partway down the pit and basically cut a hole through the bulkhead and then used the Shelby tube through that hole. And this little dotted rectangle is the location of the open part of the borehole where the mud is being injected. The mud was injected with a displacement pump, so at a constant flow rate, so that we could track the whole pressure time history. These little wooden blocks here are so we can trace the motion of the ground surface using particle image velocimetry. I have a colleague, Andy Take, who has introduced that to us maybe 14 years ago now, and this is just bread and butter for us now and has transformed the way we monitor deformations. Now, we're going to look in a little bit detail at one experiment. It's an experiment where this is the mud pressure history, mud pressure here in kilopascals versus time on this axis. You can see this experiment took about 145 seconds, so between 2 and 3 minutes. Haitao actually did this experiment at time at 3 orders of magnitude. So he did it 10 times faster than this, so it just took seconds. And he did it 10 times slower than this, so that it took about 40 minutes or something. Can't remember exactly, 30 minutes. And what we found is that according to the scale and the materials that we were dealing with, it made no difference to the outcome. So it was time independent. Now, I'm not saying that will always be the case, but certainly for the experiments we did, forget about time. And he's identified 4 different points here, specific pressure values, and I'm going to stop the experiment in essence at those 4 times, and we're going to look at what's going on. And we're going to look at the ground surface taken from a camera that he had fixed up and taking photographs continuously. And this is at the peak pressure. So you can see the pressure rapidly increases to this peak, and then there's this post-peak response down to here. And if you stop the experiment right there, which he did on one particular occasion, you can exhume this dry sand and just leave the wet sand that's in the vicinity of the borehole. And if you do that, you find that at this peak point, the only mud that's actually in the sand is this little cylinder of material or annulus of material around the borehole where the mud has been infused into that zone. Okay, and I'll show you a picture of that in a couple of minutes. When you look at the surface of the ground, you can see absolutely nothing. And if you, in terms of mud or anything, there's no mud visible. And if you measure the deflections, you find the deflections are like 0.1 millimeters. They're essentially zero. If you go to this point, then this is what you see, and you get the initiation of a crack along the surface. And Hightower's called that the primary crack. And there's some secondary cracks we'll see in a moment. And the reason for that crack is that we're getting more mud being pushed into the material, and now we're starting to get surface uplift. And that surface uplift is causing curvature at the surface, and if you like, tension on the surface, and there's a tensile fracture. It's logical. And then if you stop at this point, which we actually didn't do, but we can speculate, there's clearly initiation of flow from this sort of cylinder, and this initiation of shear planes up to the surface. And then we see a whole bunch of additional cracks that Hightower's not surprisingly called secondary cracks. And then at the very end, suddenly the pressure drops and the mud appears out here, which is a little bit surprising. With all this cracking, you'd think the mud would have come up through those cracks, but no, it never does. It comes up over here. Actually, what along, and we'll see this in the next slide, is a shear plane. So let's look at that slide I've been promising you for the last 90 seconds. Now I'm going to deliver. Here's the borehole. And this is after all the dry sand has been exhumed. Here's this cylinder of saturated clay, clay saturated sand around the borehole. We can see a few what we've called protrusions. So it's like little attempts by the mud to sort of get away from the borehole, but only one of them has really succeeded. And if you cut this one, which Hightower's done and shown in this picture, you get what he's calling a flow tube. And if you have a look at that, it's actually like it looks like a borehole actually, but it's actually an erosion tube where the sand has been washed out, and it's like there's quite a bit of mud flow through that tube. And then it flows up into what's very clearly, when you look at it in real life, it's a bit harder to see in a flat photograph, but is a shear plane. And if you do a cross section of that shear plane, it looks a little bit like a peanut butter sandwich. And there's a little layer of bread, or if you like, mud infused sand beneath and above. So they're the two pieces of bread. And then in the middle, there's a layer of pure bentonite, or if you like, peanut butter. And it's clear that the mud has flowed up that shear plane, and that the lifting of that wedge of soil is generating shear, maybe dilation or something, and then up goes the mud. Now, let's start thinking about what parameters are controlling that peak mud pressure. And on this plot, maximum mud pressure is plotted versus the burial depth divided by the borehole diameter. Now, this particular experiment that I was just showing you had an H/D ratio of just under 18. And so from this particular plot that we've just seen, you take the peak and then you plot it here. And if you're willing to work for some months in the lab and do all this hard work, which I'm very pleased to say Hightower was willing to do, you get a whole series of points, and then it becomes pretty clear what the relationship between normalized burial depth and maximum mud pressure is. Now, I haven't got time to talk to you about computer modeling of this phenomenon, but I can say that once you've got experiments, then you've got some confidence that you can develop computer models that will have some credibility and some authority, because you've got measured values and you also have seen what's happening. To do that, he started by doing three-dimensional analysis to understand the boundary conditions of his experiment, because it's not a very long borehole. It was a reasonably short borehole. And then once he confirmed that the full three-dimensional analysis was working well and matching the experiments, then he was able to say, okay, let's look at very long boreholes. That means 2D analysis. He did a parametric study, where he's got measurements, or sorry, calculated values of maximum mud pressure normalized by the effective overburden stress, a function of friction angle where that was varied between 30 and 50 degrees, the coefficient of lateral earth pressure at rest between 0.4 and 1, and then, as I said before, burial depths, normalized burial depths between 5 and 50. And then with those finite element values, you can do some creative curve fitting and come up with an expression that captures those numerical results. And so this little equation here is not derived by solving differential equations or something. We've got numerical calculations and we're curve fitting to numerical calculations. And it seems to be pretty effective. And as I said, it's just been, actually this equation has previously been published. And by the way, if there's any of the work that I'm presenting this evening, if people want the details, just send me an email, find me on the internet, find my email address, send me an email, tell me what you'd like, and I'm very happy to provide you with copies of those publications. Now, I think anybody can pretty much program something like that into a spreadsheet. So hopefully that's useful. Now, I wanted to summarize this little bit of stuff on study of mud loss in sands and add a couple more comments. I've told you there was a parametric solution. Critical pressures depended on these parameters. Hightower also did tests of some simple stratified systems. So he tested with loose layers over dense and with dense layers over loose. And the question is, what controls? Well, the material around the borehole is the most important, but the other material can also be important. So if the material over the top is weaker than the material around the borehole, that will actually reduce the strength compared to a complete system where it was just that denser material. And he's developed a correction factor based on the experiments, which he then modeled with the computer and so on. If you have dense over loose, then the loose material is going to govern and you don't get much additional strength, very little. And in fact, you just ignore it. It's just, it's reasonable and safe just to ignore the stronger material above and just consider it being uniform. Now, the final comment I'd make is about surface uplift. And that is that there are consultants and researchers who have decided that we can predict ground movement by simply modeling the borehole and modeling a fluid pressure on the inside of that borehole, just as a static stress in a finite element calculation, and then use the modulus of the soil and so on and calculate how much movement there is. And if you do that, you predict a tiny fraction of what actual displacements occur. So that's a very unconservative, unsafe approach to take to estimating ground deformation. And the reason for that is it's completely ignoring the volume of fluid that's been injected into the sand. And it's that volume of fluid, and we sort of saw that in the experiments, that's precipitating all of this movement. So if you're very concerned about deformation, do not use this type of technique to make an estimate of how much deformation is going to occur. Let's talk about mud loss in clays. This is the work of Matt Kennedy, Hongwei Xia, Haital Lan. Some of you may remember Matt because he lived and worked here in Burnaby for a number of years where he was working with Golda. Again, the objective is to understand and quantify the mechanisms of mud loss. In this particular case, because we can have either tensile fracture or blowout, trying to understand what controls. And the bad news is what controls is K0. Now, why do I say bad news? Well, it's because in geotechnical engineering, we're really good at some things. We're really good at estimating things like SU, undrained shear strength, and phi. You know, we don't nail it, but that's our bread and butter, right? K0? No. We're not good at estimating K0. And yet, and normally it's not a problem because K0 is often, unless you're doing tunneling or something, it's often not that important. But it's absolutely critical in this particular case. So that's a little bit of bad news for you tonight. We want to quantify the effects of the existing stress levels and vertical stress, and if you like, K naught or sigma H, as well as the undrained shear strength. Again, the objective is to develop tools that engineers can use and provide guidance on projects. Now, this is the only page of equations I'm going to show you tonight, and I don't have time or the inclination to take you through and explain these equations. If you're interested, I can provide the papers where they've been published. The purpose of me showing you this page of equations is to tell you that they exist and that they're not that complicated, and that with a few hours of effort, you can program them into a spreadsheet. And let's look at the 4 equations. There's an equation for blowout for K naught less than 1. There's an equation for blowout for K naught greater than 1. There's an equation for tensile fracture for K naught less than 1 and for K naught greater than 1. And so 4 equations for the 4 different sort of mechanisms, if you like, or versions of failure that you can have. Now, what I am going to talk to you about is the implications of those equations and how K naught influences which of those equations is controlling. And on this plot, I'm plotting calculated maximum slurry pressure or maximum mud pressure. And on this axis, I've got the K naught value ranging from 0.5 up to 2.5. So that's a pretty broad range of K naught values. And then this set of calculations is specifically for a borehole of 0.2 meter diameter, 5 meters below the surface, unit weight of soil. I don't know why I chose 16. It's low. It should be something like 18 for a 40 kilopascal undrained shear strength. But anyway, that's the value I chose. And then a mud density of about 13 kilonewton per meter cubed. Now, let's look at what each of these parts of this relation or this set of results is. So first of all, this central section is the blowout condition. And over here, if K naught is less than 1, we get blowout or shear failure initiating at the crown and the invert. Probably more likely the crown because the stress conditions are a bit lower there. If we have K naught greater than 1, then the shear failure will initiate at the spring lines. Okay? And those 2 different solutions that I had on the previous page would produce these 2 different lines. If K naught is very much less than 1, but not crazily low, like this is like 0.7 or something, so a normally consolidated clay could have a K naught down there, right? Then we can get initiation at the spring line, and you can see the tensile fracture condition is definitely weaker than the blowout condition. But it can only happen once we get a reasonable way away from K naught of 1. And then if K naught is very large, in this particular instance 2 or more, then we can also get tensile fracture initiating at the crown. Now, how do we figure out K naught? Well, it's going to be a function of overconsolidation ratio. It's going to be a function of the stress history of the material. We know that, let's say we're going under a river. Okay, we're looking at the sediments under a river. Well, the river's caused erosion, right? So if they're relatively new sediments, there's likely to be some degree of overconsolidation in that particular location, right? So maybe not very much, I don't know. But the point I'm trying to make is we have to use our geotechnical expertise to try and estimate what K naught is. Now, if you happen to have a self-boring pressure meter, of course, you can deploy it. But that would be for an exceptional project, I think. But there are projects that are exceptional that'll cost hundreds of thousands if you get it wrong, or millions if you get it wrong. And so maybe there are circumstances where you would deploy a pressure meter if you had one. I wanted to finish up this little part of the presentation by talking about what I'm going to present as the state of practice and the state of the art. And the state of practice is that contractors don't talk to geotechnical engineers. They use a very Mickey Mouse guideline to estimate what the mud pressure is that they can use without mud loss. And this is 1 psi per foot of burial depth of the borehole. Now you can see this line completely ignores the effect of K naught. It completely ignores the H over D ratio. It's just depth. That's the only thing it's thinking about is depth. It completely ignores the shear strength of the material. It completely ignores what mechanism might be controlling the behavior. But of course, it's great for contractors. And if they can get away with it, and if inadvertent returns aren't going to get them their pants suit off, I guess, you know, maybe that's not a bad approach. Up here is what's the result you would get if you used the so-called Delft solution. Now, the Delft solution is a cavity expansion solution for shear failure or blowout, which is based on an isotropic initial stress condition. In other words, K0 equals 1. And you can see that that equals the more general solution that Hongwei Jia developed as part of his PhD. And it will produce the right answer only if you've got K equals 1. Any other K, it will produce an unsafe result. And that's one of the take-homes that's also a little bit depressing, because people have been trying to be a bit more sophisticated and they're saying, oh, we'll use the Delft solution. Now, there are people using the equations I've been presenting to you, but a lot of the consultants who get involved are actually using this equation up here, and unfortunately, it has some drawbacks. So in conclusion, as a geotech, you'd be estimating SU. Unfortunately, you're going to have to think about K0. I haven't shown you that there is a simple criterion that Matt Kennedy developed as part of his master's project that allows you to decide, it's a simple equation or an inequality that allows you to decide, is it blowout or is it tensile fracture? It's in his paper. I haven't got time to present it tonight. I've shown you the closed form equations to estimate the maximum pressure, and I've made some rather disparaging remarks about the state of practice and the state of the art. Let's move on to deteriorated pipes. Here's some slip lining being grouted. Here's a cured in place liner being installed into a cast iron water pipe. Here's the sprayed liner system that we were studying at Queen's. These are all things that I've studied in detail, predominantly structural engineering problems. If you're interested in those things, I've done a lot of work in that area, and I'd be very happy to interact with you by email. But this is not the structural mechanics of trenchless construction, it's the geomechanics. And so the topic I've chosen to present to you is soil deterioration, okay? And so basically what happens is the pipe is broken, the pipe starts to leak, water comes into the pipe because many of our pipes are below the water table, and it causes erosion. And if you let it get too big, this is what happened in Ottawa about 4 years ago. The headline in the newspaper said, sinkhole swallows car. The poor bastard, the poor bloke who was in the car was left climbing out. Other fellow Canadians had to rescue him out, and maybe they wouldn't have been saying "you poor bastard." They would have been saying some sort of more Canadian figure of speech. But when it gets to this stage, it's too late. Okay, so the rest of my talk, I'm going to be discussing erosion voids on this topic, which are in the state of formation. And I'm going to talk about what is the impact on the pipe, and what is the impact, very briefly, the impact on the strength of the overlying road. Okay, so if a sinkhole happens under a field, it's not it's a bit distressing, but it's not that bad. But it's when it happens under highways that it's particularly challenging. And this particular structure was a steel culvert which had corroded, which had ingress of groundwater, and which had produced erosion. And this is the best photo I've ever been able to obtain at a site. In that particular site, I was able to look down the spring line through the embankment and get what I think is a reasonably good photograph. But it's fairly typical of what I've seen in terms of erosion voids forming around the spring lines. And I'm going to, there's been 3 student projects that I've had studying this phenomenon. Jean Tan, who did some computer analysis, we were essentially doing numerical experiments. And we said, let's just hypothesize some sort of first approximation void geometries. And what do those voids do to the pipe? And so the little pink void, the little yellow void, the blue void, as it grows, how does it affect a rigid pipe? And so this is some discussion of concrete or clay pipe, the effect of this type of erosion. The reason for that is that deterioration of rigid pipes is often dominated by joint leakage and erosion, not material degradation of the concrete. It's normally leakage that causes the problem. There's been some full-scale work done by Jane Peter, who finished her PhD last year. She studied a number of trenchless things, but one of them was concrete pipes with erosion voids. This shows an experiment set up in our West Pit at Queen's, half of the facility that in fact Andrea helped to develop as part of her master's thesis a bit over a decade ago. And basically Jane has used a first approximation simulated void. We artificially created a void and we said, what does it do? Because anything that, of course, that comes from a computer is guilty until proven innocent. We don't believe it. And particularly when it's a sort of rough as guts approximation like this. So we need to get some physical evidence. And then very recently, Van Meij has just finished his PhD. And towards the end of his PhD, he did some small scale perspex or Lexan box experiments where we were able to actually saturate the ground, have water flowing in through perforations, and we could watch the erosion develop. Now, very small scale, I think quarter scale, it's in terms of, it's the smallest corrugated pipe we could find. And we're currently doing some larger scale experiments. But I'm only going to present the results of Jean Tan and Jane Peter this evening because of the time constraints. So let's look at a summary of Jean's analysis, or the most important things in terms of what I'm trying to say tonight. And that is a graph of moment increase versus the size of the void. Now, maybe I'll start by talking about void angle. So the most important impact or characteristic of erosion void influence on the pipe is the fact that the pipe is losing soil support on the sides. And it's the size of that contact where the void is in contact with the outside surface of the pipe that is the most convenient way of defining the geometry. The width also has some impact and produces some variation in the results, but the most dominant thing is the contact angle. So this pink one has a 30-degree angle to the axis, 60-degree angle, 90-degree angle. So 30 degree, 60 degree, 90 degree. Then on this axis, increase in moment. Now, why moment? Because rigid pipe design is controlled by bending moment. What's the bending moment demand? What's the resisting bending moment? And if it's a unreinforced rigid pipe, like a clay pipe or an unreinforced concrete pipe, we design with a factor of safety of 2, which means a 100% increase in moment will break the pipe. If it's a reinforced concrete pipe, we design with a factor of safety of 1.5. But the design limit state is crack width. It's not collapse, it's crack width. And so if we have a 50% increase in moment in a reinforced concrete structure, we'll have exceeded the design limits, and that then may compromise the long-term service life of the structure. If it's a rigid pipe, an unreinforced structure, 100% increase will cause it to break and collapse, okay? So this is the range of values you'd calculate if you look at different strengths, like is it coarse grain backfill? Is it fine grain backfill? Is it dense? Is it loose? Is it a wide void? Is it a narrow void? You get this type of range. And essentially what happens is you're losing this side support and it's becoming just a ring under vertical load, and this will basically double, triple, quadruple the bending moments. So let's go to Jane's experiments, and I've only got time to talk very briefly about that, just like the rest of the topics tonight. But this shows one of Jane's pipes. It's got optical fiber, which is we're now using routinely to measure strain, and you'll see why in a moment. But we're also some conventional gauges. We're also using particle image velocimeter to monitor crack width, actually a technology that a previous student that Dr. Holt and I, because this was co-supervised by Neil Holt, we had a student, Katrina McDougall, who developed the ability to monitor crack widths in these pipes while we do these experiments. But we're not going to talk about that because that's structural engineering. We're just going to look at voids. And this shows a picture of Jane's one of her test setups. And we're trying to get 2 for the price of 1, actually 3 for the price of 1, because these are not cheap experiments to configure. Here's an erosion void that's being simulated. So how did we do that? Well, we got in the car, we drove to Canadian Tire, as we do, because we're Canadians, and we went in and bought the cheapest blow-up air mattress we could get. Not the sort that we would sleep on as adults, the sort we would put our children on, okay? And we strapped it to the side of this pipe, and then we covered it with geosynthetic, just so that, the soil wouldn't get in behind it. Then we bury it. Once it's buried, there are holes pre-drilled in the concrete, and then we just stick a needle through and puncture it. The bladder, sorry, it's not a Canadian Tire thing. It's a sophisticated bladder that we've introduced, air bladder, and it will collapse and fall to the bottom of the void. So very simple. Again, I emphasize first approximation void. It's not created by erosion. It's created by us making it with an airbag. But still, it's going to give us some experimental information, and it's going to be valuable. Notice there's a standpipe here. And I said we're going to have 3 for the price of 1. This is the second thing, I guess, for the price of 1. And that is, having measured what the bending moments are in the pipe with the void, we can then fill it with grout and then do another experiment and see whether grout returns it to its intact soil condition. And then the third condition is that intact condition. And that's what this pipe's over here for. All of Jane's experiments were based on using a wheel pair. So we're just representing the effect of a single pair of wheels at the end of a truck axle, okay? And we're saying, what does that single pair of wheels do? Well, it's load spreading. That load spreading, if it's up, if the surface loads here, will be just within 1 barrel of the pipe. So there's not going to be a lot of interaction between these two, and we're going to try and get as much as we can with our money. This is the only set of results of Jane's results I've got time to show you, but it's a plot of the bending moments around the circumference of the pipe on this polar plot. And there's 2 sets of bending moments. One is when there's a small void, and that's this void down here. Basically, once you've grouted it, you can see the void geometry. So one of the other attributes of actually testing and then grouting it is you get to see the grout and what the void geometry was. So that's the small void. Here's the intact soil. And so the small void 3.2, intact soil 1.9. So we've got 1 ratio of void versus intact, and we can figure out what the increase in erosion in moment was. And so here's our plot again. And so just that one little experiment that I showed you produces 1 point. Now, we learned a lot more than just that 1 point. But on this, for the purposes tonight, I'm just showing you that point. And you can see here the void because that's the actual sample that was pulled out and so on. So it gives us some encouragement that it's in the same ballpark. Now, it's a different type of loading condition. Jean's was for earth loads. This is for vehicle loads. But it's, you know, it's sort of similar, and it's sort of giving us some confidence that maybe we can sort of estimate what the impact of the erosion void would be on the damage to the pipe. Now, as I provide some conclusions on this topic, I just wanted to add a couple of points. The large void, which was basically 2 air mattresses strapped together, and a void that was 135 degrees, was so large that it compromised, and it didn't extend very far from the pipe, but nevertheless it was sufficiently large that it compromised the load carrying capacity of our unpaved road that we're simulating in the lab. And we could not get the wheel pair up to the full service load. So we've got some nice experimental data on strength loss or compromised strength due to an erosion void. And I've currently got a PhD student who's modeling all this on the computer. When you re-grout the system, and I'm showing you the large void moment because that was the worst case, actually you get back to just 30% more than the attack case. So it's much higher, and then it drops down to 30% higher, which if you think about that plot, and the factors of safety isn't really a concern. And it actually turns out it's within the load capacity for this particular example that's required in North America. So that grouting with aerated grout that we used was quite effective. And there's a picture of the pit we're now using, one that there's somebody in the audience here who's got a little bit of experience with at West Campus, which we're going to be doing saturated ground testing with full-scale concrete pipes, specifically to look at three-dimensional void geometry, because the voids we've studied so far are all sort of prismatic, but if you've got erosion into a joint, the void geometry is not prismatic, it's three-dimensional. So it's going to be a second generation, or maybe even a third level of approximation. So my final topic, pipe bursting. Here's a typical static pipe bursting rig in operation in Illinois at a field site where we were studying pipe bursting in clay. It's difficult to prepare big masses of clay in the laboratory, so we tend to do that in the field. Here's the burst head that's about to be pulled through by a series of links that are attached to this pulling machine. Behind the static burst head, or the expander as it's often called, is a polyethylene pipe that's been attached. The outside diameter of that expander is greater than the inside diameter of the clay pipe that we're going to replace. So it basically breaks that clay pipe apart, pushes the fragments out, and then you've got room to pull in the new polyethylene pipe. This work from VG Fernando, who I think some of you probably know because he's a local here. Michael Kemetag, Heather McLeod, who also I think has worked here, although I think she's moved up into Northwest Territories now. John Haliva and Kazi Rahman, but I'm just going to show you, I've only got time to show you one experiment of John's and Kazi's analysis of that experiment. And here's John's experiment. Here's the expander. Here's the new pipe being pulled into place. And there's a concrete pipe that's being replaced with a polyethylene pipe in this experiment. This is in our east pit. The pit's 8 meters long, 8 meters wide, and 3 meters deep. We're measuring on the ground surface the uplift because we're interested in the ground disturbance associated with this phenomenon. And we're also interested in how it disturbs this pressure pipe that John has put running transverse to the sewer. Because there's been quite a few instances where pressure pipes have been broken, which if it's a water main, that could be a problem. If it's a gas line, it's a big problem. And there's been explosions and fatalities, and there's certainly been floods and various things. So we need to think about this other infrastructure. And currently, if the contractor's concerned, they will excavate a trench and basically uncover that pressure pipe. And the pipe there is no longer in the ground, it's sort of hanging in the air. And so the ground then can move and it won't damage the pipe. But the purpose of trenchless construction is to not construct trenches, right? And so we'd rather not do that if we had to. If we have a way of estimating the deformations and determining whether that adjacent utility is in danger, we can save money. Here's John installing his concrete pipe. Here's his PVC water pipe. This was a decade ago, so we weren't using optical fibers. We relied on a series of strain gauges attached along the top of the crown and the invert of that pipe. And basically, by monitoring those gauges, we can find out how much longitudinal bending is happening in that PVC pipe. And then by integrating the curvatures from that longitudinal bending, we can get deflection. Here's the ground surface. We're monitoring with more wooden blocks and total stations. Again, Andy, I think this is the first project I worked with Andy where we used his PIV or DIC technology to get surface deformation. Here's the reaction pit where the pulling machine is and is recovering the pulling rods. So I've got 3 sets of results, or 2 kinds of results I wanted to show you as I finish this evening. This one is the strain measured along the top of the water pipe. So with a series of strain gauges on the top of the PVC pipe, we've got a series of readings of strain. Here's the midpoint of the pipe. That midpoint of the pipe is directly where it crosses over the old sewer, right? That's being replaced. And we would expect it to be symmetric because what's happening on the right should be a mirror image of what's happening on the left. And it's, you know, it's reasonably symmetric. So that's encouraging. This little cartoon shows where the burst head or the expander is relative to the pipe. And as we look at the next one and the expander's moved closer, of course, the strains have increased. And if we're right under the water pipe, we get these values. And then actually the peaks, interestingly, form just after the expander has passed the water pipe. Okay? And so we've got a nice set of readings that we can use in various sorts of calculations. So let's look at some calculations. These are not predictions. You know, you can't predict things by doing the calculation afterwards. If we could, I'd make millions off the global financial crisis. Tomorrow I'd be predicting that we had a GFC or the global meltdown 10 years ago and I'd be a billionaire the day after. But of course, that's not real prediction. That's just, you know, being a pundit, I suppose. But these are post-test calculations performed with independently measured soil parameters. So no fiddling of parameters to curve fit, but not predictions. Here's the concrete pipe. Here's the water pipe. We have to model, I say we have to. Of course, I didn't have to do anything except ask Kazi to do all this really difficult analysis. So Kazi had to model the burst head. This is the geometry of the burst head. Here's the new polyethylene pipe. And he has to model the propagation of that all the way through here and the failure of the existing sewer and the whole three-dimensional behavior. It has to be geometrically nonlinear because the cavity is expanding quite significantly. Of course, it has to be materially nonlinear. And it's a huge sort of nonlinear interaction problem. So it's not an easy analysis to perform. One thing you need to do to capture the right soil behavior is you need to model dilation. So here's volume strain, here's shear strain, there's the sort of triaxial test curve, and there's Kazi's approximation to that curve. And it's important that you don't just use constant dilation angle because the level of shear strain in this sort of circumstance is enormous. And we actually get up to the critical void ratio, like the limiting void ratio, or the sort of the minimum density, I guess, once you dilate a dense material, and you'd get a very conservative calculation if you just went straight up, waltzing straight up here. So if you do all that and you're a little bit lucky, you get calculations that match the predictions like this. We didn't quite, something strange happened to the measurements directly over the sewer, but otherwise the PVC pipe strains along the crown and the invert of the PVC pipe were pretty good. So we've got a pretty good confidence that this analysis is going to give us the behavior of some adjacent infrastructure if we want to do a parametric study, which in fact Kazi did do. Let's look at contours of uplift movement. This is the experimental measurements that John produced, and this is Kazi's calculations. Now there's some similarities here and there's some differences. So let's start with the similarities. The peak uplift was exactly the same. I mean, again, a little bit of a fluke here. We were lucky to get so close. As we know in geomechanics, it's not easy to get that close, partly because we're doing a controlled experiment with known materials at known densities. Like, these are ideal conditions for doing a calculation, but pretty good in terms of the maximum value. Pretty small because this is a dense sandy gravel, like a really good road base type material. But could be big enough to break a metal pipe if there was a metal pipe down there, because you don't need a lot of curvature depending on the type of pipe you're dealing with. But so that's pretty good. Now look at a difference. So with the experiments, the peak is here, the burst head is here, and you can see the peak is just behind that, just like I mentioned. But notice how then it drops. It doesn't go up to the peak and then stay constant, it drops. So basically the burst head goes, it rises, and then the soil surface drops. Whereas the calculation is good at predicting the maximum peak, but it can't produce that settlement back down after the burst head has changed. So if you wanted to use this analysis to predict, is a pressure pipe going to break, which is going to be a function of the maximum movements, the analysis is good. If you want to use it to predict, is my railway is my roadway going to be out of alignment, then it's going to give you a conservative answer. Now, maybe CN or the TTC or somebody, or I don't even know the name of your railway here in town, but the authorities looking after those things probably don't even want you to consider the residual. They want to just focus on the peak. But I'm just pointing out the fact that the analysis is not capable of doing the unloading correctly. Some conclusions. Extensive zone of shear failure develops in the vicinity of this cavity expansion. So if you actually calculate the volume being displaced down here by the burst head, and you calculate the volume of material being lifted up at the surface, this volume is massive compared to this volume. Like it's 20, 30, 40 times bigger. Because most of the volume increase is because of dilation. It's not because of the fact that we've sort of pushed some volume out here. Well, it sort of indirectly is. This is causing the shear failure, right? But you can't just say, okay, I'm going to get that volume and that's going to tell me the total volume up here. No, it's the shear failure. And so if you know the density characteristics of that soil, if it happened to be at the critical void ratio, yay, there's going to be almost no movement, right? If it's loose, there's going to be settlement. That can actually be a problem in certain circumstances. If it's dense, there's going to be uplift. So just knowing that means that as a geotech, you can sort of say, okay, I've got an idea as to what the basic behaviors are going to be and whether I need to chase it or not. Finite element modeling, I mentioned that you must limit dilation. Kazi's done a parametric study. It's not very extensive, but it's certainly a parametric study which allows us to make various sorts of predictions. But there are things that still need study, like pavements, layering, sloping ground. You know, there's still some work to do, but there is some tools there that you can go. And again, if you're interested, contact me. I'll give you copies of the material that will give you some guideline. So in general, there's lots of trenchless technologies, and there's more every year. They're good for minimizing surface disruption, and they can produce repairs, replacements, and new installations. The idea of the research is to produce guidance that geotechs and also structural engineers, which I haven't talked about tonight, the structures, can then engineer these problems correctly, rather than just being, let's just do it all empirically because the contractor's going to look after it. Well, that can be okay, and it may not be okay. Analyses after experiments are really useful for explaining the phenomena, but also producing parametric studies that, like charts, equations, and so on. And I've illustrated that tonight. I've tried to emphasize my graduate students, as I always do when I'm making these presentations. I'd like to also mention Richard Brackman, Neil Holt, and Andy Take, who are my colleagues at Queen's, David Chapman, visiting professor from Birmingham, and Graham Skinner, who were co-supervising students. Graham Boyd, who's has been my awesome lab guy. The other funding agencies. But again, I'd just like to thank Contech, Tetra Tech, Thurber, and Clone Crippen Berger and the Foundation for Geotechnique for this opportunity to be here and to have so much fun for 2 weeks crossing this beautiful country of ours. Thank you. Wow. I think as I'm going on, I'm getting slower. I'm getting more into my stride and having more fun, which means that I'm taking more time. So I'm looking at the clock there. You've been very patient, so I thank you for that. And if you're still not completely out of patience, I'd be very happy to.